When power system disturbances occur such as faults, line switching, or sudden load changes, power swings may develop. If these swings become too large, generators can lose synchronism with one another. Out-of-step OOS protection was developed to detect these conditions rapidly and take appropriate action to separate asynchronous areas. Modern advancements have improved the accuracy and speed of OOS detection and the coordination of protective schemes, ultimately enhancing system security and reliability. The United States power grid has experienced several major disturbances in recent years, including the massive blackout on August 14, 2003, and significant events in 1996 that affected millions of customers. These events typically occurred when the grid was heavily loaded, and multiple outages happened in rapid succession, causing oscillations between neighboring utilities, voltage drops, and eventually instabilities in both voltage and phase angles. Fully designing a system to prevent such rare, simultaneous outages is prohibitively expensive, so utilities implement special protection systems (SPS) and remedial action schemes, such as under-frequency under-voltage load shedding and controlled tripping of loads or generation, to reduce the impact of disturbances. Out-of-step protection for generators gained attention after major blackouts, including the 1965 Northeast power failure and the 2003 blackout. In response, industry groups developed guidelines and technical standards for setting OOS relays to ensure system stability. OOS occurs when a generator loses synchronism with the power system due to disturbances or malfunctions in its automatic voltage regulator (AVR). This condition can lead to high peak currents, mechanical stresses, and pulsating torques, potentially requiring the generator's separation from the system via out-of-step tripping relays. If the disturbance is mild, the system stabilizes with oscillations in the generator's load angle. Power swing blocking PSB relays are used to prevent unnecessary tripping during stable power swings, ensuring unaffected generators and transmission lines remain connected. During normal operation, a generator maintains a constant speed because the electrical torque it produces balances the mechanical torque applied to its rotor. When a fault reduces the transmitted power, the resulting drop in electrical torque while the mechanical power remains unchanged causes the rotor to accelerate. Consider a two-source power system initially at a balance point angle transferring power. After a fault, the output drops to PF, leading to rotor acceleration and an increase in delta. When the fault is cleared at delta C, the now higher electrical power output PC creates a decelerating torque because PC exceeds P0. However, due to the rotor's inertia, the angle continues to rise to delta F, where the energy gain during acceleration exactly matches the energy loss during deceleration, a condition known as the equal area criterion. If delta F stays below a specific limit delta L, the system is transiently stable and with sufficient damping will eventually return to its original balance at delta 0. But if delta F exceeds delta L, the decelerating energy is insufficient to counter the ongoing mechanical input, and the rotor continues to accelerate uncontrollably. This results in a loss of synchronism, meaning one part of the system rotates at a different speed than the other, leading to transient instability. Power system stability means that after a disturbance, be it a fault, load change, or generator disconnection, the system can return to a stable operating condition. The system's integrity is maintained if only the faulty parts are isolated, while the remainder continues to operate normally. In cases where generators or system areas lose synchronism, it becomes crucial to immediately separate those zones to prevent widespread outages and equipment damage. One effective mitigation strategy is controlled islanding, achieved through two complementary out-of-step protection schemes. Out-of-step tripping, this targets predetermined network locations to disconnect system areas that are experiencing unstable power swings, thereby preventing further outages. Out-of-step blocking, this scheme ensures that distance relays or similar protective devices do not operate incorrectly during power swings, restricting separation actions only to the desired locations. When disturbances hit a power system, their impact depends on both the system's current operating condition and the disturbance's intensity. A fault on a critical component once isolated by protective relays leads to fluctuations in power flows, bus voltages, and generator rotor speeds. These fluctuations trigger responses from voltage regulators and speed governors in the system. Based on the disturbance's severity and how the system's protective measures react, the system might either settle into a new equilibrium, a stable power swing, or become transiently unstable. In the unstable scenario, substantial differences in generator rotor angles occur along with large swings in power flow and significant voltage and current fluctuations, ultimately causing generators or interconnected systems to lose synchronism. When two areas of a power system lose synchronism, the entire network experiences extreme variations. In phase operation results in high voltages and low currents, while a 180-degree phase difference produces low voltages and high currents, leading to severe system disturbances. The principles behind these schemes and examines the performance requirements for distance relays during out-of-step conditions, highlighting challenges such as defending against unbalanced external faults and ensuring that only the affected phase is tripped during a fault, rather than all phases. Under normal, steady-state conditions, all synchronous generators in a power system operate near their nominal frequency, balancing mechanical torque with their electrical output. If disturbed, differences in generator speeds result in changes to rotor angles. Initially, the system self-corrects by shifting loads between generators. However, if the angular difference becomes too large, power transfer decreases, which can lead to sustained instability. Loss of synchronism, or an out-of-step condition, impacts transmission line relays differently. Some relay systems like segregated line differential relays remain unresponsive during these events, while others such as overcurrent, directional overcurrent, and distance relays may react to changes in voltage, current, and phase angle relationships. In some cases, these relays might even trigger during stable power swings from which the system can ultimately recover. For example, instantaneous phase overcurrent relays will activate if the line current during a swing surpasses their minimum threshold. Similarly, directional instantaneous overcurrent relays will operate if both the current and the phase relationships align appropriately, whereas time overcurrent relays typically remain inactive, though their response depends on current magnitude and delay settings. Phase distance relays work by measuring the positive sequence impedance for faults of value that varies with the phase angle separation between system sources during an out-of-step event. These relays will engage if the swing causes the impedance locus to enter their operating characteristic. Zone 1 elements, without any time delay, are especially sensitive, and Zone 2 elements in pilot relaying schemes are also prone to activation. Conversely, backup zone elements, owing to their time delays, often do not operate during swings. The operation of distance relays during power swings hinges critically on the interplay between the relay's polarizing memory and the measured voltages and currents. Modern microprocessor-based distance relays that include frequency tracking are less affected by polarization memory rotation. Additionally, if the line's positive sequence impedance is high relative to the system's impedance, these relays may operate during swings even during conditions from which the system could otherwise stabilize. Some out-of-step tripping OST relays provide only tripping functionality, while others also include power swing blocking PSB capability.